Welcome to the final part of my second lecture. In this part we will discuss the third application of Monte Carlo simulation. And in this application, I will illustrate properties of ordinary least square estimator. Namely, I will focus on so-called Gauss-Markov theorem. You can find this theorem over here, but also on the website where I uploaded this theorem. Basically this theorem states that OLS estimator is blue, which means that this is the best unbiased estimator in the class of linear estimators. To illustrate this property, we will study the behavior of three different estimators. All of them are linear, and I will show you that what does it mean that estimator is unbiased, and if both estimators are unbiased, which estimator is better in terms of variance of the estimate. So that's the plan for the very last part of this lecture, of not this course but this lecture. That's it. In this exercise, we are interested in statistical properties of OLS estimator and relative advantages of this estimator to other estimators. In our exercise, we will organize a horse race between different estimators, and apart from OLS, we will use also ordinary ridge regression, least absolute deviation regression, those will be those three estimators that we study in this exercise. To analyze those estimators, we will use Monte Carlo method in a bit different way than before. In this exercise, we will play a role of data gods. That we will know what is the true data generating process. We will know that how X affects Y. So we will know this data generating process, and then we will generate these examples of this relationship by generating some observations, and then using simulated data sets, we will use our estimators to see how those estimators reveals estimates of true parameters using generated data. So we will do it not only one time, because for each estimator will be used. So we will generate our samples, our data sets, many times. So for each realization of data set, we will use estimator once, and we will repeat this many times to see how this the estimated values of using our estimators vary across different simulations. So right now it may sound very abstract, but I hope that when we start solving this problem, it will be a bit more intuitive. So let's start doing this. So the first comment that I should make before we start is that we will use quasi-random number generator, and we will simulate random numbers. Actually, those numbers are not so random because we can replicate them. And what I mean by this, if I run runif, and if you run this on your computer, it's very unlikely that you will get exactly the same numbers as I did here. Yeah, but now, from time to time, for replicability of our studies, if we want to say that, yeah, we observe this and we want to have evidence that if somebody wants to check whether we're saying true, then we can set so-called seed. And this number, if we set seed and we run the same code on different machines, we should get exactly the same results. Yeah. So here, if we set seed equal to 12, for instance, yeah, it can be any number. And if I type runif here, or for instance runif, yeah, I generate 10 numbers, I will get this. And if I reset the seed to 12 once again, I will get sorry, yeah, here I got different numbers than before because I haven't set seed to the same level. And now if I set seed to 12, then if I run this runif once again, I should get exactly the same numbers like here. Yeah, let's see. Yeah, you see, those numbers are exactly the same. And also on your computer, I think that on Macs and other Unix-like systems, they should be exactly the same. On Windows, it's super likely that they will be the same. Okay? Yeah. So in this exercise, we will use run quasi-random number generators, yeah, to generate our data. If you want to have the same results as I'm gonna have, then you have to set the seed to the same number. If you want to have some surprises, then yeah, then you can set to different values. Yeah. So here we have seed, and what is next is that we will need one package that it's not installed by default. Yeah, quantrec. Yeah, because less absolute deviation regression is particular is one of cases of quantile regression. Yeah, package quantrec is for quantile regression. Yeah, and let's install this. Yeah, okay, it was fast, and we will need, and now we can load this library. Also, we will need library mass, where we will use function ginf, which is, yeah, here as you can see, it is from package mass that we loaded, and this package invert matrices. Yeah, because at some point we will need to invert matrices. And let's load one additional library that we already know. Progress. Yeah, and this allows us to create progress bar, because in this Monte Carlo simulation we will create one very large for loop. Yeah, and yeah, to know what's the progress, yeah, let's use progress bar. Yeah, on top of this. Okay. Yeah. So this is it. Yeah, and now in this step we define our data generating process. Okay, and let's suppose that here we are interested. Yeah, so let's, in this experiment, let's use a simple linear regression. We have some, this will be our intercept. Yeah, so let's have intercept at the level, yeah, I will set it to 25. Yeah, and beta, so this true parameter, this slope of the relationship between x and y, let's keep it at, let's use 12. And in our simulation, in each simulation, we will use only 25 observations. Yeah, so in each time, each of our estimators will estimate on a very small sample, but between different simulations, we will make, we will generate new data sets. Okay, so this is it. Yeah, and let's set number of simulations. Let's use, let's say, 100,000. Yeah. So I'm loading this to the memory, and those are parameters of the simulation that don't change across different simulations. So those are, and in particular, perfect world, on the basis of our data, we would like to have estimator that pin down those two parameters, yeah, exactly at the level of 25 and 12. Those are true numbers, yeah. And now we can generate. So now let's generate data using those parameters. Now let's create objects vectors that will store estimates of all our simulations. Yeah, and let's create the first object, slope OLS, and this will be numeric vector of length simulations. Yeah, and let's do it the same thing with ordinary ridge regression and with lateral regression. Yeah, and in our exercise, so there are closed form solution for this estimator for OLS and the ordinary ridge regression. The formulas for those estimators you can find over there, yeah, over down, and we will use those closed form solutions, but also just to check, yeah, whether we will get the same results. We will use also for OLS, we will use LM, the function for linear models that we already know, and and this is it for those two estimators. And for LID estimator, there is no closed form solution, so for this reason we will use a command from Quandrec package. Yeah, so that's those objects will store our estimates. Yeah, and now let's create axis. So our variable that will be on right hand side, and let's generate the n observations from interval. Yeah, I will use intervals from interval 0, 10. Yeah, I'm using uniform distribution, and if we take the Gauss-Markov theorem very seriously, in assumptions of this theorem, we have assumption that regressor, those covariates are deterministic. Yeah, so let's assume that in each simulation we will have exactly the same values of x. Yeah, and the only thing that will change across simulations will be additional noise and the sum of noise, this innate uncertainty, and deterministic relationship between x and y, the sum of those two things will give rise to realization of y. Yeah, so here we create those numbers. Yeah, most likely, if you set c to the same value, you should get exactly the same values. Yeah, and now, if we take those formulas from down there, if we want to estimate intercept, our alpha parameter, we have to create matrix that consists of our x, but also the column of ones. Yeah, so let's create this x, capital X, as c bind of 1 and x, small x. Yeah, so this is it. Now let's use, let's simulate data only once, and also let's make only one estimate, one estimation for each estimator. Yeah, and we have our x, and now from our data generating process, we assume that there is some that the relationship between y and x is that there is some constant plus beta. Yeah, so our constant was 25, I guess. Yeah, our intercept is 12. Yeah, so this is the impact of x on our impact of x on our y on average, but also we assume that there is some stochastic indeterministic part. Stochastic and indeterministic is the same, yeah, but some part which is not explained by the relationship between x and y. Yeah, and to generate this uncertainty, we will draw some random numbers from normal distributions, I guess. Yeah, from normal distribution, we will draw n, the same number of observations as the number of observations for x, and let's use that this is 0 mean and with standard deviation equal to 5. Yeah. Yeah, and now we have relationship. We have generated y and x, and if we plot y against x's, yeah, you see that here we have some different values of x's and some positive relationship. This positive relationship, the true that we know that what we should generate, it should be 12, but because of some noise, our estimator can be disguised, can be confused, yeah, by this to pin down exactly beta equal to 12. Yeah, if we can also add line, we can use this this function that we discussed before to plot color orange, to plot the true relationship. Yeah, this is the true relationship that we would like to pin down using those observations. Yeah, and now, yeah, we will use this with 3 estimators. So first use function lm, which computes, which uses OLS estimator to pin down the relationship between x and y. So this will be our first method that we're using. Yeah, and here you see that if we run regression of y against x's, we get something here. It's quite. It's not 12. It's not 25 as desired here, but somehow it is not that far. Yeah, because the level of noise here is not very large. Yeah, and also if we type summary, if you remind. If you remember, this returns also some additional tests. We see that both estimates, intercept, and our slope are statistically significant, statistically different from zero. Yeah, and now if we want to store the result of this estimation, if we write coef and then this model, this returns our coefficients. And here, in this case, we are interested only in the second argument, yeah, because in the simulation we're interested how we could store those two values, yeah, but in this Monte Carlo experiment we will study only the behavior of slope, yeah, how this slope is estimated for many simulations, yeah. So if we type this, yeah, we get this coef. If you remember, if we write unnamed, then we get rid of x. I hope so. Yeah, exactly. And now we can use, if we want to store this result, the result of this simulation, to the first element of slope OLS, we will use something like this. Yeah, and here slope OLS. If I type this, it will be super long, but if I want to use if I want to observe the very first observations, yeah, and this is it. Yeah, as I said before, we can estimate our coefficients using OLS using either function lm that we know, or this mathematical formula from down there, and essentially, yeah, we should get exactly the same results. If we don't get those the same results, something is wrong with our code, yeah, or functions that we're using, but most likely with our code. And now, so let's use this function. Yeah, you have prime, which accounts for transposition. Yeah, in R we use this T. So if we want to write this mathematical formula in matrix notation in R, we will use not small x but capital X, and that's the first element. That's the first element from down there, and we want to multiply this with normal x, and matrix multiplication can be conducted using this. Yeah, so that's the first the first factor in this formula, but still we have to invert this matrix, and for this purpose we will use ginf. Yeah, this function invert our matrix. Yeah, so this -1 this object is raised to the power of -1, which means matrix inversion, by putting this as argument of function this ginf, and then we get some matrix, but it's not the end. Yeah, because right now we will use also, here we have tx and this x transpose times y. Yeah, and okay, so now those are numbers obtained using LM function, and yeah, we get exactly the same numbers. Yeah, because we use the same method. We use the same estimator using two approaches. Yeah, so if we want to store only our slope, we have to call what? The second row, the first column. Sorry. If we here we got mistake because R wasn't sure whether we want to have second row and the first column of this matrix or the whole object. Yeah, so if I put bracket here, everything is fine. Yeah, and this is it. Okay, slope LS2. Yeah, we start this. Estimates for the ridge regression can be achieved using this another mathematical formula. Yeah, and basically the only difference is that here, instead of inverting this matrix, we will invert this matrix plus some scalar on the diagonal. Yeah, because there, as you can see, there is lambda times I. I is identity matrix, and identity matrix of here we want to have an identity matrix of size of with 2 rows and 2 columns. We will get using this, and let's use in this simulation, let's use lambda equal to, yeah, we'll talk in the next lectures. We will talk how to choose this regularization parameter lambda. Yeah, but here we will use some value 1 plus 1.5. Yeah, and we will add this here. Yeah, and then essentially it will be here we get a bit different estimates than for ordinary less square regression for OLS. Still, it's not that far yet from 12. Yeah, but yeah, from one simulation, yeah, we cannot say a lot about properties of this ridge regression. Last but not least, we will estimate the same relationship using LAD, least absolute deviation, and this type of regression is exactly equivalent to quantile regression, in which we are interested in median, in modeling median. Yeah, and without discussing those properties of this estimator, it's enough for you to know that we will use function RQ. Yeah, it is RQ. RQ, and we are interested in this, in modeling this relationship. Without one also it works. And now, if we want to obtain our coefficients, we can work in exactly the same way as in the first OLS estimate. With the use of coef, we want to have this, and we want to get rid of this x. Yeah, and this is it. Yeah, so now we have this one. Yeah, and so now we have 3 estimators, 4 methods, because for OLS we have 2 methods, and now we are in the position to compare those estimators using Monte Carlo simulation. Yeah, so here in this example we use this only, we generate this data Y only once, but now we will do it how many times? So many times. Yeah, it's 100,000. Yeah, so that's the plan for the next part of this lecture. Now, in this Monte Carlo simulation, we will repeat this data generating process. So we won't change axis, we keep it fixed, and the only thing that will change is Y, and this will be changed by drawing new realization of noise. Okay, so now we will generate a loop, for loop, with i's from 2 to n simulations, y from 2, because already we computed this, our first simulation, and inside this loop, first we will generate new relationship between relationship is the same, alpha and beta will be the same for each simulation. We will draw those new numbers, and effectively it will change also values of y. So now, and we want to repeat this. So now we want to check those how those estimators work for different realization of x and y, and here the only thing that we have to change is that we change element I of those vectors. Yeah, so more or less, here, because every time this is updated, those guys are not changed, and perfectly we want to have with our estimates to get as close as possible to beta. But we know this as data guts, so this is the step where we know was the beta, but now in those lines we close our eyes and we are econometricians that try to identify this beta. Yeah, so that's more or less that's the plan for this for loop, and the only thing that we will need to update is to generate progress bar. Now we will introduce this progress bar that I mentioned before. This is from package library, and we generate this progress bar, new. Here we provide how many steps we have in our for loop. Actually, we provide how many steps we have, and here we have n simulations minus 1. Yes, so to be very precise, we should write n simulations minus 1, because this is number of steps. If we want, and here we update this with command tick. And this is the code that it may take a while to run. We will see. And Yeah, also I want to, yeah, for some people that are more advanced in Monte Carlo simulation, in particular this and this step could be extracted outside the loop. Yeah, but I wanted to for didactic purposes. Yeah, I keep it here. Yeah, so okay. Yeah, so now let's run it and let's see whether it works. Okay, now I will speed up this. Yes. Okay, sorry. So now, yeah, it took a while, yeah, to simulate this, yeah, and now we have slope less, yeah, and we have a lot of different estimation of our estimators for different realization of y. Okay, and in particular we can compare. So let's compare first to those two estimators, slope or less. On average, on average we choose almost 12. Yeah, so this suggests that our estimator is unbiased. The same thing is for least absolute deviation. Okay, and for all error, yeah, here on average this number, yeah, this is, yeah, it's not almost 12. Yeah, it's not that far. Yeah, but here we see that there is some bias. Yeah, if we increase this n to even a larger number, this average realization of OLS and LID would be super close to 12. But ridge regression, yeah, at some point there would be some limit that there would that we wouldn't get to 12 and closer. Yeah, so this is the first observation. Now we can let's plot first OLS and this and LID. So here I change parameters that I want to have two plots in one plotting area. Yeah, and first let's create the slope OLS, color medium purple, and yeah, I ran that simulation before, so let's set this x limits for this interval. Yeah, and what I'm doing is that I want to make those two histograms comparable. Yeah, so I want to so I set exactly the same x-axis and the same y-axis for OLS and LID. Yeah, and I think that okay, something wrong. Okay, it's wrong because I set frequency here to 2500. Yeah, and we should increase this here because we have much more observations. Yeah. Yeah. Here, yeah, it's not so visible yeah, but here OLS, yeah, the probability mass here should be higher than here. Yeah, you see that here those bars are higher. Yeah, so on average the variance, the realization of least absolute deviation, yeah, it should be yeah, it should be scattered for the wider region. Yeah, so on average both realization, the average value of OLS and LID is 12 or something super close to 12, but as you can see, yeah, for OLS, yeah, we have the lowest, the smallest bar is for 11, while here there are still some realization below 11. Yeah, and the same thing for 13. Yeah, so it's the variance of LID is larger. Yeah, so that's the observation, that both estimators are unbiased, but OLS is better. Yeah, because we are getting closer to our true parameter. I agree that in this histogram, this difference between LID and OLS is not so visible, but still this difference is substantial. Yeah, and if we compare the variance of this estimator with the variance of our OLS estimator, yeah, the difference should be substantial. Yeah, indeed. Here you see that the variance of LID estimator is by 50% in relative terms is by 50% higher than the variance of OLS. Okay, yeah, and the very last thing that we're gonna to show is we will plot the same. In addition to those plots, we will plot this, and yeah, and I changed number of figures on the plot to 3. Yeah, you see that here essentially the very large probability mass focus on somewhere close to 12.5, yeah, which clearly shows that here there is some bias of this ridge regression. Yeah, and yeah, it is widely known that ridge regression estimator is biased. Yeah, and here clearly it is visible. Yeah, but on the other hand, if we compare the variance of OLS regression and ridge regression, actually I should before, yeah, let's put OLS yeah, to make it just like with comparison with LID. We see that here the variance of the ridge regression is smaller. Yeah, so on average we miss the true value, but on the other hand more points are focused. Yeah, so this range of realized estimates is smaller. Yeah, so there is this trade-off, yeah, that we can use unbiased estimator with higher variance or less, or we may be aware of bias, but with this bias we can buy lower variance. Yeah, and essentially this will be one of topics, yeah, that from time to time this ridge regression is not as bad as as we would think in a standard econometric course. Yeah, and in the statistical learning, ridge regression is one of those models that may be fine. Yeah, and but we will discuss this in the next lecture. This concludes my second lecture of this course. In lecture 3, I will introduce some first topics related to statistical learning, but the next lecture will. But before that, the next lecture will start with presenting my solutions to the assignment that I ask you to at least to try to solve on your own. You can solve this assignment over here, yeah, and please, before playing the next lecture, try to solve this on your own, yeah, and then compare the solutions that you had with my solution, yeah, and so this will be the first part, and then yeah, it will be only statistical learning, yeah. Okay, so have a nice evening, whatever daytime you're watching this. Yeah, so see ya, ciao.